term. We focus on dominant term. So non-dominant term, we can safely erase. For example, this one, non-dominant term, we can erase it. Okay, yeah, all right. So dominant term. But for the dominant term, there is another part I like to, make your thinking going that way. Yeah, that is, remember, we introduced the concept called order of growth. Order of growth concept. Here's the question, what's the order of growth, right? Let me give you the specific number order of growth. Yeah. All right. For n squared, order of growth is this 2. N to the certain exponent, that number we call order of growth. Okay. Yeah. And 1. Order of growth 1. All right. This is hard. Yeah, this is a hard one. All right. Yeah. This is hard one. Okay. Log. The question is, what is order of growth of log? That's hard to answer. Okay. Yeah. Yeah. All right. So here, the reason is this. When you have a function, power function, the order of growth is easy. Power function n to the dth power. So then the order of growth d, order of growth. Okay, straightforward. Yeah. But if for non-power function, it's hard. Exponential function, log function, then it's hard. Okay, yeah. So for your thinking, yeah, for your thinking, right, in calculus, you know epsilon delta language, right? You know a little regarding epsilon delta language in calculus when we, yeah, epsilon delta language, okay, yeah. So, yeah, so here I do not go completely that kind of language, but I want to borrow that epsilon concept here. Borrow it, epsilon concept. You know epsilon, right? Epsilon, very special symbol. Okay, yeah. We can make it very small, right? Arbitrary small, epsilon. Okay, here I want to borrow that epsilon notation. So log of n, we can treat it as n to the epsilon. N to the epsilon. But what's the epsilon? This epsilon, we treat it as less than, greater than 0. Epsilon must be a positive number. It cannot be 0. Okay? But less than any positive number d. Whatever positive number you make d, epsilon is smaller than that. 0.0, many 100 zeros for d, our epsilon is still smaller than that. You use this epsilon for your thinking, okay? For your thinking. Now when you do comparison, this one you can use n to the epsilon. That one you can use 1 plus epsilon, right? Because 1 times log, 1 plus epsilon. And now you can compare the order of growth, right? The first one is 1, second one epsilon, third one is 1 plus epsilon, fourth one is 2. You can do comparisons, right? Yeah. For number 11, can you do simplification first? N squared takes square root. Okay, so that's n to the first. Order of growth 1, right? Yeah. Here, this is very large. Okay. Exponential function, you know how large. Okay. Here, for me, yeah, for me, it's hard to, yeah, we infinity, but infinity, yeah, the order could, yeah, you can think of infinity. Okay, the order, yeah, because when you compare, that order is is greater than any positive number. Any positive number. Right. Factorial is, close to e to the nth power. Yeah, close to. Okay. Yeah. So we can connect to it. Yeah, factorial. All right. So this one, C, you can use that epsilon. Is it 1 minus epsilon? Because log at the denominator, right? Can you do 1 minus epsilon? Okay. Yeah. So this, we cross out log because plus, right? Plus we can cross out. Okay. So n to the first. Can you do comparison? Can you do comparison? Right? Think about that. Order of growth. Order of growth. Yeah. Try to use epsilon, but this epsilon has the special property. This is special property. A little abstract. A little abstract. But we need some abstraction. Yeah. We need to use some abstraction. Yeah. All right. Number 12, similar, right? Yeah, number 12, you can use the similar way to answer number 12 question. Yeah.
I see it now.
Yeah, you see it, right? Now you can do comparison A and B. You use epsilon. Epsilon. Okay. Yeah.